I'm making a video today on some chemical equations because some people asked about it. So here it is, all the equations you need for IB Chemistry HL. So keep in mind that this video will purely be on equations and that there's other stuff than just equations to do well in chemistry. But I still think that this video will be useful for you guys. So let's start with topic 1 or chapter 1, stoichiometry. This chapter is mostly about converting stuff into moles. So let's start with the first equation, which is the basics of moles, how to turn number of particles into moles, or the other way around here, turning moles into number of particles. So if you want the number of particles, you just multiply the number of moles you have by Avogadro's number. And if you want to go from number of particles to moles, you just divide by the number of particles by Avogadro's number. Just rearrange the equation. Alright, the next one is converting moles into mass. And this is done with this equation. Moles equals mass over molar mass. Or if this is hard to remember, you can rearrange the equation into molar mass equals mass over moles, because it's easier to see the units this way, because the units of molar mass is mass over moles, or grams per moles, which is easy to see by this relationship here. But this one, where you convert mass into moles, is the most used one. So I would definitely remember this equation. The next equation here is converting concentration into moles, or the other way around, where we have concentration and volume. So the moles equals the concentration times the volume. And the way to remember this is either to remember the equation or just to remember the units, where concentration has the units moles per cubic decimeter, and volume has volume decimeters, so they cancel each other out, so you end up with moles. Yeah. So this is also very important for titrations and stuff, where you often have to convert volume and concentration into moles. This equation is for dilutions, because when you dilute something, you don't change the number of moles, but you do change the concentration and the volume. So by holding the moles constant, you can equate the moles at the beginning and the moles in the end. So this way you can make the moles not change, but the volumes and concentrations can change. So when you increase the volume, you decrease the concentration. So yeah, this one is sometimes useful for titrations, but mostly it's useful for just general dilutions. So those were the equations for mole conversions. So now we go over to percentage yield. And it's quite simple to calculate the percentage yield. It's just the experimental yield over the theoretical yield, where the theoretical yield is the maximum calculated yield you can get, and the experimental is the yield you get from the experimental, or the experiment. Alright, so next part is the ideal gas law, or gas behavior. So the ideal gas law is PV equals nRT, which is in the data booklet, and it's very important for, well, gas behavior in general. So pressure times volume equals moles times the gas constant times the temperature. And just as with dilutions, when you do something to a gas, the number of moles stays constant. Like if you heat up a gas, you just increase the temperature, but the moles, you don't add or remove moles. So you can once again equate the number of moles when you change variables, or when you do something to gases, so that the moles in the beginning equal the moles in the end. And you see that the R is not here because it's a constant, so you can just cancel on both sides. So this equation is for when you change a variable in a gas. For example, if you start with a pressure 1 and then you increase it to a pressure 2, and then you want to see how temperature changes, you can use this equation. Now there's also a equation to calculate the moles at STP, which is the volume of the gas divided by the molar volume as at the STP, which I think is 22.7. It's in the data booklet if you want to see it for yourself. It's just a convenient way to do it, but it really just comes from the ideal gas law. Because if you insert the variables at STP, you just get the volume for 1 mole as 22.7. So these are the equations for chapter 1, and I also added the variables here. So yeah, next chapter, chapter 2, atomic structure. Not really a lot of formulas, but there are two. And the first one is how to calculate relative average mass. It looks pretty scary because I condensed it into a sum. But it's just the sum of the masses of the isotopes times the number of the isotopes divided by the number of particles altogether. For example, for chlorine, you have two different types of isotopes. You have chlorine 35 and chlorine 37. And let's say that you have 70, or per 100 atoms, you have 70 of the 35 and 30 of the 37. You just take 35 times 70, and then plus 37 plus 30, and then divided by 100, and then you get the relative average mass. So it's basically just a way to average the mass from the ratios of isotopes. Right, the next equation is the photon energy, and this is related to energy level transitions. For example, if you have a ground state and then an excited state, and then you shine some light on it, or energy, and then a electron can transfer or transition higher up in states, and then when it falls back, it's going to release a photon with some energy. And this photon energy is calculated by h v. I don't think it's v, I think it's a Greek letter, I just don't remember. Nu or something. Anyways, but it's frequency. So it's the Planck's constant times frequency. And there's also a equation which is called the wave equation for electromagnetic radiation, which is that c, or the speed of light, equals the frequency times the wavelength. And if you rearrange that, you get that v, or the frequency, equals the speed of light over wavelength. So if you substitute that into the equation, you get that the photon energy equals Planck's constant times the speed of light over the wavelength of the electromagnetic wave. So this equation is sometimes used. I don't see it too much, but it's good to know anyways. And it's quite simple to remember. Planck's constant is in the data booklet, and so is the speed of light. Okay, next one, chapter 4, because there weren't any questions in chapter 3. Chapter 4 is chemical bonding and structure, and there's really just one equation, and it's how to calculate formal charge. And the equation is that formal charge equals the number of valence electrons in a non-bonded atom minus the sum of the non-bonding electrons plus the bonding electrons divided by 2. So I thought I would put an example here because it's a bit hard to explain otherwise. So we have a carbon dioxide molecule here, and we want to figure out the formal charge on the different atoms. So the point of formal charge is to figure out the electron distribution within a Lewis structure. So the goals is that you want the most electronegative atom to have to carry the negative formal charge if there's a negative formal charge, and you want to minimize the formal charge, and you want the formal charge to match the overall charge of the atom, or the molecule, I mean. And in this case, carbon dioxide is neutral, so there's not supposed to be any charges, and since we want to minimize it, we want them all to be 0. So let's check that they're all 0. For carbon, we know that it's number 6 in the periodic table, so it has 2 in the inner shell and 4 electrons in the outer shell. So valence electrons equals 4, and then we subtract the non-bonding electrons, which in this case is 0 because they're all bonding, and then the bonding electrons divided by 2, and this is basically the same as how many bonds it has, because for each bond there's 2 electrons. So we have 8 bonding electrons divided by 2 equals 4. So we get 4 minus 0 plus 4, which is 0. So carbon has a formal charge of 0. And we can do the same for oxygen, and these two are identical, by the way, so we can just show it with one. Oxygen has 6 valence electrons, and here we have 4 non-bonding electrons. So now we have 6 minus 4, and then 2, or 4 technically, for bonding electrons divided by 2 equals 2. So we have 4 plus 2 here, so 6 minus 6 equals 0. So the formal charge of oxygen is also 0. So this works out. Yeah. Next chapter, chapter 5, energetics and thermochemistry. We have quite a lot of equations there, and they usually always come up for tests. So it's quite important to know the equations in this chapter. So the first one for SL is heat transfer. So the equation here is Q equals mc delta T. I've heard people remember it as MCAT. So I guess that's one way to do it. And so Q is the heat transfer, M is the mass, C is heat capacity, and T is the change in temperature. Now for exams, the typical question is usually that you heat, or you have a reaction in a water container, and then you get how much water you have and the temperature change of the water. So the mass of the water would be the M, and the change of temperature would be the delta T, and the C would be the heat capacity of water, which is 4.18 grams per liter, I believe. So if you divide both the sides by the moles, you get enthalpy, because it has the, or molar enthalpy, I guess. Yeah, because it has the units kilojoules, or just joules per mole. So just divide the heat transfer by the number of moles, and then you get delta H. And the next thing is enthalpies of reaction. So if you have a reaction, most reactions would either release or absorb heat. And you should know by now that reactions that release heat are called exothermic, and the ones that absorb heat are endothermic. So the way to calculate the change in enthalpy is just the sum, or there's two ways actually. The first one is with enthalpies of formation, and the second one is for bond enthalpies. So with enthalpies of formation, you usually would have to look in the data booklet, because of different molecules have different enthalpies of formation. And it's also important to remember that, like, molecules which are found in their natural state, for example oxygen, O2, and H2 and all of that, they have a hydrogen enthalpy of formation of 0. So the equation is just the sum of the enthalpies of formation of the product minus the sum of the enthalpies of formation for the reactants. I usually just remember products minus reactants, because it comes up quite a lot. Now for bond enthalpies, it's basically the same. It's just the sum of the bonds broken minus the sum of the bonds formed. And if you want to find the bond enthalpies, you also have to look in the data booklet. So the way I remember this is that forming bonds releases energy. So if you have more energy released when you form the bonds, it means that, or like, if the energy is for forming bonds is greater than the energy you need to break the bonds, it would become exothermic, and this would only occur if you subtract the bonds formed. So it's broken minus formed. And okay, now let's go over to the HL part. And the difference here is that we also have something called entropy. So the equation for entropy is basically the same as the one for enthalpy. And also keep in mind that these are at standard temperature, pressure, which is why you have a theta sign here. So the question is also product minus reactants for entropy. And now we have this quantity called Gibbs free energy, which is used to determine spontaneity. And the equation is delta H minus T delta S, where delta S is the entropy. And when delta G is negative, it means that the reaction is spontaneous. And the way to remember this is just to think of the reaction diagrams, where if you have your reactants here and your products here, if it goes downwards, it's spontaneous, or that's at least how I remember it. It's not necessarily like that, but it's just simple to remember. So when delta G is less than 0, it's spontaneous. If it's more than 0, it's not spontaneous. And if it's 0, it's in equilibrium. And usually for these kinds of the problems involving this equation, you would have to determine if a reaction is spontaneous or not. And then you just, like, if you want it to be spontaneous, just put this less than 0 and then rearrange and then find the temperature. Oh yeah, the question is like, at what temperature is the reaction spontaneous? And then you just put the whole equation less than 0, and then you rearrange, and then you solve for T, which would be the temperature at which the reaction is spontaneous. Right, next chapter, chapter 6, kinetics. It's a pretty simple chapter, or at least for SL, it's pretty simple for the equations, because all you need to know is how to solve rate equations. So for a 0th order reaction, which is the reaction which doesn't depend on the concentration of anything, the rate would be just a constant, because it wouldn't depend on anything. So R equals constant, and the constant, it changes from reaction to reaction, so it has to be experimentally determined. For a first order reaction, it depends on one of the reactants, for a reaction where you have A plus B equals products. So in this case, it would just depend on the concentration of A. And for a second order, it would depend on the concentration of A and B. So yeah, usually in a problem you would have some data where you have to determine the rate equations. Now for HL we have two quite complicated equations there, which are fortunately both in the data booklet. So you just need to know what the different quantities mean. For this equation, it's called a Arrhenius equation, and it's used to, I think it's usually used to either find the reaction constant or activation energy. It's either one of those. So you have this A constant, which is called the Arrhenius constant, which accounts for collision frequency and the geometry of the collisions, I think. It's basically just a proportionality constant. And then you have this EA, which is the activation energy, which is the energy needed for a reaction to occur. So this is usually either given or you're supposed to solve for it. And then you have gas constants and temperature. And then, yeah, that's basically it for this equation. The next equation is if you have data and you want to find, like you do two different experiments and then you get 1K, or like you do two different experiments at two different temperatures. And then if you do that, you get 1K for one temperature and another K for another temperature. And then if you graph it, you can use the gradient to find the activation energy. So if you just rearrange for activation energy here, you get, well, I guess activation energy from the K1, K2 and T1, T2. So it's a bit hard to remember this equation, so just find it in the data booklet. Alright, chapter 7, equilibrium. Pretty simple chapter when it comes to equations. So there's basically just two things you need to know for SL, and it's how to calculate the equilibrium constant and the reaction quotient. So for a reaction where you have A plus B goes to C and D, and then you have the stoichiometric constants A, small b, small c, and small d, the equilibrium constant is calculated as the concentrations of the products multiplied and the concentration of the reactants multiplied to the power of the stoichiometric constants. And it's the same for the reaction quotients, but the equilibrium constant is calculated when the concentrations are at equilibrium, and the quotient is calculated for any point in the reaction. So the point with the quotient is to find how far the equilibrium has come. So if the quotient is the same as the constant, it means that it is at equilibrium. If it's less than the equilibrium constant, it means that we'll go towards the equilibrium constant, or we go to the right, the forwards direction. Now if the quotient is larger than the equilibrium constant, it means that it will decrease, which is the backward direction. So that's it for SL. For HL, we just need to know the relation between delta G, Gibbs free energy, and the equilibrium constant, and it's related by this equation, which is in the data booklet, where delta G equals minus gas constant times temperature times the log of K. So you may know that the equilibrium constant only changes with T. Like nothing else can change the equilibrium constant except temperature. And it's clear from this reaction, because delta G is also only dependent on T, and like properties of the reaction, for example, or namely enthalpy and entropy. So the K value only depends on temperature, which is clear from this equation. So yeah, next chapter, assisted basis, the most heavy chapter on calculations. So we do have a lot of calculations, and especially for HL for this chapter. So the basics is just the definition of pH, where pH is the negative logarithm of the hydrogen or proton concentration. Now, if we want to find the concentration of protons instead of just the pH, we can rearrange the equation by dividing by -1 and then taking the power of 10 to the power of what we have on the left side here, and it rearranges to this equation, where hydrogen plus concentration equals 10 to the minus pH. Now there's also this thing called the water dissociation constant, which is this Kw, and it's equal to the products of H plus times OH minus. And at I don't remember if it's room temperature or standard STP. I think it's STP, where the water dissociation constant is 10 to the minus 14. So that's usually when you would do calculations. Otherwise, it's supposed to be stated. But I do think there's a table where it shows the variation of Kw with temperature. So you just find the correct value, and then if you have the value for proton concentration, you can then find the value of OH minus concentration and vice versa by knowing the Kv. You just divide by both sides. Now that's it for standard level basically. So now we go over to the hard part, which is HL. And there's two things there's basically just two new things for HL, and it's this thing called Ka and this thing called pKa. Now pKa is basically just the negative log of K, but I'll still go through all the equations. The first one is this. I think this is the most basic one, even though I put it as the second one. But it's Ka equals proton concentration or hydronium ion concentration times the conjugate acid divided by the concentration of acid. So this is for weak bases, by the way, because weak bases don't fully dissociate. And this is from the reaction here, where I have a genetic acid here and water, which is protonates, and then you get the conjugate acid. So the K is basically just the equilibrium constant there. So it's these two multiplied divided by the acid, and for the Ka, it's technically the equilibrium constant times the concentration of water. So the concentration of water would usually be here, but you just multiply it with the K to get Ka. So all the Ka and Kb is basically just a equilibrium constant. So that's a easy part to understand what Ka is. And then it should also be easy to understand the strength of acids and bases, because if a weak base dissociates a lot, the Ka turns quite big, which means that stronger weak bases have a larger Ka than weak bases. No, acids, I mean. And it's the same for bases, or Kb, but for bases instead, where you have a generic base and conjugate acid of the base. So let's go over to pK, pKa, and pKb. pK is just a negative log of the Ka, which means that if you have a very strong acid, you would have a small exponent, for example 10 to the minus 1 would be a pretty strong weak acid. Now if you take the minus log of the K, then you would get a smaller number than if it was weak. For example, a weak acid could have something like a equilibrium constant as 10 to the minus 20 would be a pretty weak acid. Now the pKa of this would then be 20. So the lower pKa you have, the stronger acid, and the lower Ka you have, the weaker acid. So they're kind of opposite. Now the same is true for pKb, where you just use Kb instead of Ka. Now you have this relation, pKw equals pK, which is basically the same as pKw equals pH plus pOH, which comes from here. You just take the negative log of both sides. So this equation would usually just say pH plus pOH equals 14, because at standard SDP, the pK or the kW is 10 to the minus 14. So if you take the negative log, you get 14. So it's one way to convert between pH and pOH. And it's the same to convert between pKa and pKb. So yeah, that's all the questions for acids and bases. Now redox processes. There's really just two very important equations for this chapter. The last one comes up sometimes, and it's important to know, but I don't know how frequently it comes up. So the cell potentials, at least, come up all the time, and it's a part of the SL syllabus. So the cell potential is calculated as the half cell where the reduction occurs minus the reduction potential of the reduction reaction minus the electron potential of the oxidation reaction. So what this really says is just that when you write two half equations, you have the reduction equation and the oxidation equation, but in the data booklet they're all written as reduction reactions. So if you want the potential of the oxidation reaction, you have to flip the reduction reaction because it goes backwards, and by flipping the reduction reaction you have to change the sign of the reduction potential. So it's really the reduction potential minus the oxidation potential, but you get this by taking the negative reduction potential of the oxidation reaction. So I just remember this as E cell equals E red minus E ox. And this is important to understand how to do with problems and stuff, because it comes up all the time. And the thing with the E cell is the same as delta G. If the cell potential, no, it's the opposite of delta G. If the cell potential is negative, the reaction is not spontaneous, and if it's positive, it's spontaneous. And this is clear from this equation, which is HL, where delta G is the negative of NFE. So if E cell is negative, you have negative multiplied by negative, which is positive, which makes delta G positive and then spontaneous. Now the N here is a constant, which is the number of electrons transferred in the reaction. For example, if you have a simple reduction, for example copper 2 plus 2 electrons goes to copper, then this N would be 2, because you have 2 electrons transferred per reaction, I guess. And F would be the Faraday constant, which is the charge of 1 mole of electrons. and its values found in the data booklet. So that's this equation. I think it's usually used in problems to figure out the delta G and not the E cell. So you would have a problem where you had to find the E cell, and then the next problem would be to find the delta G. Now the next equation, it's a bit of a rare one, but it's used to find the mass deposited on the cathode for a electrolysis experiment. So for example, if you're trying to electroplate the cathode, you would want to know how much current you would need to apply for how long to deposit a certain amount of mass on the cathode. So I think it's a bit of complicated formula to remember because it's not in the data booklet. So I think it's easier to remember how to get to the equation. So then the only thing you need to remember is really this relation, which is pretty simple. It's just that the charge equals current times time, or that current equals charge over time. So if you know this, you can know that the number of moles of electrons is the charge divided by Faraday's constant, because the Faraday's constant is the charge per mole of electrons. So if you flip the fraction, you get charge per mole of electrons per charge, and then you just get you get number of moles of electrons and then times charge divided by charge. So you just get the number of moles of electrons from this equation. Now the moles of the compound deposited would be the number of moles of electrons transferred divided by some constant set, which is the number of electrons transferred. For example, for the reaction I mentioned before, and the C copper 2 plus 2 electrons goes to copper, you would have to use 2 electrons per reaction. So you would then have to divide it by 2. So this would be how many moles you have of the material deposited. Now if you want to find a mass, you just use this equation I introduced in the first chapter, where mass equals moles times the molar mass. So you would then get the mass deposited as this reaction in total, MIT over ZF. I don't know how often this equation comes up, but well, now you know it. Last few equations. For chapter 10, organic chemistry, not a lot of equations, but there is one, which is the index of hydrogen deficiency, which is similar to what people would usually use, which is called double bond equivalence. It's basically to find how many hydrogens you're missing for a compound to be totally saturated. So the way to calculate this is carbon times 2 plus 2, because for a straight chain alkane you would have the number of carbons, and then you have hydrogens on both sides, plus 2 terminal hydrogens. So this is the max saturation. And then you would there's supposed to be parentheses here. You're supposed to subtract the number of nitrogen, number of hydrogen, and the number of halogens, and then divide by 2. And this way you would get the index of hydrogen deficiency. Yeah, well, I can try to make an example. If we just have something which is totally saturated, for example, let's say methane, which is CH4, and we could take the index of hydrogen deficiency, which in this case should be 0. So then we take 2 times C, which is 2, and then plus 2, which is 4, and then subtract the nitrogens, which is 0, and the halogens is 0, but we have 4 hydrogens, so it becomes 4 minus 4, and then divided by 2 is still 0. So yeah, that's how you would calculate the index of hydrogen deficiency. And then the last equations, which are not even, it's not purely chemistry, it's just data processing. So it's propagation of uncertainties. It would probably come up sometimes on a paper 1 or paper 2, I'm not sure. But for a addition or subtraction, such as C equals A plus minus B, the uncertainty or the absolute uncertainty in C would just be the absolute uncertainties of A plus B, or an absolute uncertainty of B. So it's the same if it's plus or minus. It's always the absolute values added, or absolute uncertainties added, I mean. For multiplication and division, it's similar, but in this case it's the fractional uncertainties, which is the absolute certainty over the value. So in that case you get a fractional uncertainty of C, and then if you want to find the absolute uncertainty C, then you would have to multiply this whole expression by the value of C, and then you would get the absolute value of C. Now the last equation is how to find uncertainties in exponents, such as C equals A to the power of n. And this would just be, or the fractional uncertainty C here would just be the exponent times the fractional uncertainty of A. So yeah, that's all the questions. I guess good luck on the exams and with revision, all of that. See you in the next video, I guess.